Question number 65. A multi-stage axial compressor takes in air at 1 atm 300 Kelvin and compresses it to a minimum of 5 atm. The mean blade speed is 245 meter per second. So U is 245 meter per second and work coefficient delta C theta upon U is 0.55 for each stage. For air, use Cp is equal to 1005 joule per kilogram Kelvin, R is equal to 287 joule per kilogram Kelvin and gamma is 1.4. If compression is isentropic, the number of stages required is. So inlet stagnation pressure P01 is equal to 1 atm. T01 is equal to 300 Kelvin. Pressure ratio Rp is equal to 5 by 1 because they have given minimum of 5 atm. So 5 by 1 is equal to 5. Pressure ratio is 5. Right? So let's find out increase in temperature through whole compressor. One, two, this side T01, P01, this side T02, P02. Right? Let's apply isentropic relation to find out T02 exit stagnation temperature because they have mentioned that it is isentropic. So what is isentropic relation? T02 by T01 is equal to P02 by P01 power raised to gamma minus 1 upon gamma. So that is equal to Rp raised to gamma minus 1 upon gamma. So T02 is equal to T01 300 into 5 raised to gamma is 1.4. So exit stagnation temperature T02 is equal to 475.146 Kelvin. What about delta T? That is equal to T02 minus T01. 475.146 minus 300. So delta T, change in temperature through the compressor, is equal to 175.146 Kelvin. Right? Now let's find out what is delta T for one stage. So they have given delta C theta by U is 0.55 and U is equal to 245 meter per second. Delta C theta by U is equal to 0.55. Right? We know that specific work done for one stage is equal to U into delta C theta. Right? So in place of delta C theta, we can write from here 0.55 U. So it will be 0.55 U square. Correct? So specific work done will be 0.55 into 245 square, that is equal to 33013.75 joule per kilogram. Now we know that specific work done is Cp delta T, that will be equal to 33013.75. So delta T will be equal to 13.75 upon 1005. So that is equal to 32.85 Kelvin. Right? So in one stage delta T is this much. For complete compressor delta T is this much. So number of stages will be delta T for compressor divided by delta T for one stage. So number of stage N is equal to delta T for complete compressor upon delta T for one stage. So delta T for complete compressor is 175.146. 175.146 upon 32.85. So N is equal to 5.33. So they have mentioned that round off to next higher integer, that will be 6. So total number of stages required are 6. Question number 64. An ideal ramjet is to operate with exhaust gases optimally expanded to ambient pressure at an altitude where temperature is 220 K. So ambient temperature is 220 Kelvin. The exhaust speed at the nozzle exit is 1200 meter per second at a temperature of 1100 Kelvin. So exhaust speed is 1200 meter per second and exhaust temperature T exit is equal to 1100 Kelvin. Given gamma is equal to 1.4 at 220 Kelvin, R is equal to 287 joule per kilogram Kelvin for air, and gamma is 1.33 at 1100 Kelvin. R is same only for hot exhaust gases. The cruise speed of this ramjet is, so let's find out exit Mach number, is equal to VE upon under root gamma R T exit is equal to 1200 upon under root 1.33 into 287 into 1100. So they have given 1.33 gamma for exhaust gases. So M exit is equal to 1.852. Now while studying ramjet engine, we proved that for ideal ramjet, because ideal ramjet is given, for ideal ramjet, exit Mach number and inlet Mach number both are equal, correct? Here I am not proving, we have already proved in the class. So we will just use that result. M exit is equal to M inlet. So inlet Mach number is also equal to 1.852, which is equal to VA upon under root gamma R TA, right? So let's substitute the values. 1.852 is equal to VA, we have to find out, under root gamma R is 287 and TA, ambient temperature, is 220 Kelvin. 1.852 is equal to VA upon 297.315. VA is equal to 550.62 meter per second. Now they have asked to round off to nearest integer. So answer will be VA is equal to 551 meter per second. Question number 47. A rocket operates at an absolute chamber pressure of 20 bar to produce thrust F1. The hot exhaust is optimally expanded to 1 bar absolute pressure using a convergent divergent nozzle with exit to throat area ratio AE by AT of 3.5 and thrust coefficient CF1 is equal to 1.42. The same rocket, when operated at an absolute chamber pressure of 50 bar, produces thrust F2 and thrust coefficient CF2. Which of the following statements are correct? Option A, F2 by F1 is equal to 2.5. Option B, F2 by F1 greater than 2.5. Option C, CF2 by CF1 is equal to 1. Option D, CF2 by CF1 greater than 1. So we have to find out ratio of thrust and ratio of thrust coefficient. So CF1 is equal to 1.42. PC1, chamber pressure in case 1 is equal to 20 bar. Exit pressure is equal to 1 bar. So in case 1 we have rocket. Here stagnation pressure, chamber pressure is equal to 20 bar. Exit pressure, it is optimally expanded to exit pressure of 1 bar. So ambient pressure is equal to 1 bar because it is optimally expanded. So stagnation and static pressure ratio PC by PE will be equal to 20 by 1, that is 20. So this is for case 1. For case 2, chamber pressure is different now. Chamber pressure here is 50 bar. Right? Ambient will be same 1 bar. But exit pressure will be different now. How we can find out exit pressure? This ratio PC by PE will be equal to 20. Right? So P exit will be equal to PC by 20, that is 50 by 20, 2.5 bar. Right, this is for case 2. So here exit pressure will be 2.5 bar. It is more than ambient pressure. So there is a difference between exit pressure and ambient pressure. So in this case there will be pressure thrust also. Now we can write thrust F is equal to PC AT chamber pressure into throat area bracket gamma under root 2 gamma upon gamma minus 1 bracket 1 minus PE by PC power raised to gamma minus 1 upon gamma plus PE by PC minus PA by PC bracket into AE by AT. This we have derived in the class, right? And this term, this complete term is CF, thrust coefficient CF. So we can write F is equal to PC AT into CF. Now for case 1, exit pressure is equal to ambient pressure. So this term will be 0, right? So for case 1, this complete thing is CF, right? Thrust coefficient CF1. So we can write this complete CF is equal to this thing CF1 plus PE by PC minus PA by PC into AE by AT. So CF2 will be equal to CF1, that is 1.42 plus PE minus PA upon PC. So P exit for case 2 is 2.5 minus 1 upon PC, that is 50, into AE by AT, that is 3.5. It's given. So 1.42 plus 0.105 equal to 1.525. So CF2 is equal to 1.525. So let's find out the ratio. CF2 by CF1 is equal to 1.525 upon 1.42. That is equal to 1.074. So it is greater than 1. So here in option D, CF2 by CF1 is greater than 1. Now let's find out thrust ratio. So we can write F2 is equal to PC in case 2, AT, it is same, PC AT into CF2. Similarly, F1 is equal to PC1 AT CF1. If we divide both, AT and AT will get cancelled out. We will get PC2 by PC1 into CF2 by CF1. So F2 by F1 is equal to PC2 is 50 bar upon 20 bar into CF2 by CF1 means this 1.074. So F2 by F1 is equal to 2.5 into 1.074, that is equal to 2.685. So F2 by F1 is equal to 2.685. So here in option B it is greater than 2.5. So both B and D are correct option. So here F2 by F1 is greater than 2.5. Question number 42. Which of the following is not always true for combustion process taking place in a closed system? Which is not always true, right? So first option, total number of atoms is conserved. So this is true, right? Total number will be conserved. Second option, option B, total number of molecules is conserved. This is not true, right? Because if we take the example of octane, which we had studied in the class, so 2C8H18 plus 25 O2 plus 79 by 21 N2 it gives carbon dioxide, water plus nitrogen. Right, so from here we can see that total number of molecules are changing, right? It is not conserved. So this is not true. Option C, total number of atoms of each element is conserved. This is true, right? Because on the basis of this only we are balancing the equation. So this is true. Option D, total mass is conserved. This everybody knows, right? This is universal law. So total mass for a closed system will be conserved only. So this is also true. It means option B is correct answer, because they are asking which of the following is not always true. So option B is correct. Question number 35. In a single stage turbine, the hot gases come out of stator nozzle at a speed of 500 meter per second at an angle of 70 degree with respect to the turbine axis as shown. Right, here it is 70. The design speed of rotor blade is 250 meter per second. So U is equal to 250 meter per second. The rotor blade angle beta at the leading edge is, we have to find out this angle beta. So this is very simple question. We just have to solve velocity triangle. So they have given absolute velocity 500 meter per second. So this is 500 meter per second. So we'll draw the velocity triangle as it is given in the question itself. So this is absolute velocity. So U is 250 meter per second. So this is 250 meter per second. This is relative velocity. Let's draw the axial velocity. So this angle is 70 degree. This angle is beta. We have to find out, right? This is axial velocity CA. So this is C theta. We already know this is C theta, and this much is W theta, right? So CA, axial velocity, is equal to 500 cos 70 from velocity triangle, that is equal to 171.01 meter per second, and C theta will be equal to 500 sin 70, that is equal to 469.8463 meter per second, right? So W theta will be equal to C theta minus U, 469.8463 minus 250, that is equal to 219.8463, right, meter per second. So in this triangle we can write CA tan beta is equal to W theta, right? So 171.01 tan beta is equal to W theta 219.8463. So tan beta is equal to 219.8463 upon 171.01. So beta will be equal to 52.1 degrees. Question number 34. In a static test, a turbofan engine with bypass ratio of 9 has core hot exhaust speed 1.5 times that of fan speed. The engine is operated at a fuel to air ratio of F is equal to 0.03. Both the fan and the core streams have no pressure thrust. The ratio of fan thrust to thrust from the core engine is. So they have given bypass ratio, that is beta. We know that it is the ratio of mass flow rate through fan duct and mass flow rate through core engine. So from this side, total mass flow rate, let's say it is m dot A. Now through the fan duct, it is m dot capital F, and through the core engine, which will take part in the combustion, that is m dot core, right? Here we will mix fuel, and fan exhaust speed, let's say it is V exit fan. Exhaust from core engine is V exit core. They are telling that it is static test, right? Means VA is equal to 0. Correct? Now we have to find out ratio of thrust through the fan duct and thrust through core duct. That is equal to, thrust force is rate of change of momentum. So what is outgoing momentum? So outgoing momentum for bypass duct is m dot E capital F into V exit capital F minus incoming momentum, which is 0 because VA is 0, it is static test, divided by m dot E through core VE core. So m dot E through fan duct into VE V exit fan upon this m dot E through core, we can write m dot C, and here we are mixing the fuel, so plus m dot small f, this is exit mass flow rate from core engine, into V exit core. Now from here we can take m dot C common, so it will be m dot E F VE F upon m dot C common, so it will be 1 plus m dot F upon m dot C, which we can write F, correct? Fuel to air ratio, V exit core, correct? Now this ratio is beta, so we can write thrust from fan duct divided by core thrust is equal to beta into VE fan upon 1 plus F VE core, right? This ratio V exit fan upon V exit core is given in the question itself. Here core exhaust speed 1.5 times that of fan exhaust speed. So let's substitute the value. Beta is 9 into 1 by 1.5 upon 1 plus F is 0.03. So we will get ratio is equal to 9 upon 1.03 into 1.5 is equal to 5.82. Question number 30. A high pressure ratio multi-stage axial compressor encounters an extreme loading mismatch during starting. Which of the following techniques can be used to alleviate this problem? Option A, blade cooling. So this is not the correct option because we use blade cooling in turbine and not in compressor, correct? Option B, variable angle stator vane. So this is correct option. Variable stator vanes can be used to deflect the air to change the angle of attack of blade to prevent the chances of stalling of blade, right? Blow off valve, this is also true. Blowing off the air will increase the mass flow rate, so axial velocity will increase and angle of attack of blade will reduce and it will go away from stalling. Multi-spool shaft, so this is also correct. So we can use multi-spool compressor, low pressure compressor, high pressure compressor, so that we can run different spool at different speed, correct? So these three methods were already given in the homework to read. These are employed to prevent the surging due to load mismatch. Question number 23. The reason of highest static temperature in rocket engine and reason of highest heat flux are respectively nozzle throat and nozzle entry, combustion chamber and nozzle throat, nozzle exit and nozzle throat and combustion chamber. So we know that temperature is highest inside the combustion chamber, correct? And what is the relation between stagnation and static temperature? H naught, stagnation enthalpy, is equal to static enthalpy plus V square by 2. Cp T naught is equal to Cpt plus V square by 2. So T naught is equal to T plus V square by 2 Cp, correct? In combustion chamber, velocity will be negligible. So stagnation temperature is equal to static temperature inside combustion chamber. So static temperature will be highest inside combustion chamber. So first is highest static temperature. So in option B, it is in combustion chamber, correct? So as velocity increases, static temperature decreases, correct? So highest will be inside combustion chamber and highest heat flux is at minimum area section, nozzle throat. So option B is correct.